I want to thank the organizers for giving me this chance to talk about Terahertz emission in two classes of topological materials and what kind of new physics we can learn from these two families. So the first part of my talk will be on spin injection into not a metal, but a semiconductor, and whether it is even possible. And the second part of my talk will be Terahertz emission in a semi-metal. So the first part of my talk is whether we can achieve spin injection into a single layer semiconductor, which is MOS2. And what we found is that we can actually obtain a a giant spin injection current density. And the reason why we can do that is because we make use of the far out of equilibrium properties of the spin populations. So a challenge in the spintronics community has always been whether it is possible to inject spins from a ferromagnet into a semiconductor. And because of this conductance mismatch between these two materials, the spin injection efficiency is always very low, of the order of 1%, for example. And various efforts have been done to try to increase this efficiency. So so some groups use the tunneling effect, but the efficiency is still extremely low. Some other groups use a quantum point contact, but this is only possible at very low cryogenic temperatures, and other groups use circularly polarized light. So the motivation of our work is, once again, Tobias' work in 2013. So many speakers have already talked about this, so I'm not going to belabor the point. But so we ask ourselves this question: what if we replace this heavy metal by a semiconductor? What will happen? And so when Marco was a postdoc, he suggested this scheme that even if you have a semiconductor, the spins are able to be injected into the semiconductor only if the carriers have very high energy. And the advantages of this is that you get very high efficiency, you get a very large spin current, you do not need large spin orbit coupling. The device fabrication is simple, and this is a temperature insensitive process. And this is a cartoon picture of what happens. The first step is we send in a pump pulse, and we create a strong out of equilibrium carrier distribution. And then what happens is the excited carriers diffuse towards the semiconductor side, and in the process they relax in energy. However, there's a strong spin asymmetry of the electron-electron scattering lifetimes. And so the majority spin electrons, they persist in having a high energy, while the minority spin electrons relax very quickly. And so what happens is that only those with the energy higher than the semiconductor bandgap can actually cross into the semiconductor layer. And so in effect, this semiconductor bandgap filters only the high energy carriers. And so the net effect is that we get an extremely high spin polarization of the current that's injected into the semiconductor. And so this is his theoretical prediction. So we went on to do the experiment where the semiconductor is a monolayer MOS2, and the ferromagnet is cobalt. And so as you can see here, when the sample is just a single layer MOS2, we get effectively no Terahertz emission. When it is pure cobalt, we get a little bit of Terahertz emission due to ultra-fast demagnetization. But when we put cobalt on top of MOS2, we get a very, very large Terahertz emission. So we went on to try to figure out what is the origin of this high, strong Terahertz emission. And what we found was that it is consistent with spin-to-charge conversion in that when we flip the magnetic field direction, we flip the polarity of the emitted terahertz. When we pump the sample from the front and from the back, we also get a flip of the polarity of the terahertz emission. So these two experiments are consistent with spin-to-charge conversion. And we then went on to do a pump power and wavelength dependence. So we pumped with 800 nanometers and 400 nanometers, and the x-axis is the absorbed power. If this process is a near to equilibrium process, then these two lines should actually overlap with each other. However, you can see that it is very, very different. And so we concluded that this, where we pump with 400 nanometers, there's a higher injection efficiency. So it has to somehow be related to the fact that these electrons that are pumped with 400 nanometers are very far away from equilibrium. But just taking data at these two wavelengths is not sufficient. So we did a systematic measurement where we pump from 0.5 electron volts to about 2.5 electron volts. And so you can see that at below about 0.6 eV, the Terahertz emission that we got is similar to that from cobalt. And then as we increase the pump photon energy, there's a linear increase. And then at about 1.2 eV, suddenly there's a change in slope. And the slope is actually a smaller slope. So we asked Marco, and Marco said it's easy to explain. So first, when we pump at less than 0.55 or 0.6 eV, both the spin up, the majority and minority spins, they do not have enough energy to overcome the Schottky barrier, whether it's an electron or hole Schottky barrier. So all the Terahertz emission that we got is just from pure cobalt. And in this regime, the spin-up electrons have enough energy to overcome the electron Schottky barrier, but the spin down, they do not have enough energy to overcome the whole Schottky barrier. And as you increase the energy of the pump photons here, you increase the fraction of the electrons that can go into the semiconductor layer, and so there's a linear increase here. So what happens when we pump higher than 1.2 EV? In this case, both the spin-out electrons and the spin-down holes have enough energy to overcome the electron and hole Schottky barrier, respectively. And however, the contribution to the spin current, the injected spin current from the holes is opposite to that from the electrons. And so the net effect is that you have a smaller slope here. And so this set of measurements show that this spin injection is mediated by the far out of equilibrium spin populations, and they take place inside the MOS2 layer. Why? If we add these two values, about 0.55 and 1.2, this is more or less the band gap of single layer MOS2. We then went on to calculate the magnitude of this injected spin current density. So from the Terahertz electric field strength at the detector, we work backwards. From the detector and then at the sample position, then we calculated the charge current density, and then we calculated the spin current density, and we got this conservative value of roughly 10 to the 6 amperes per centimeter square. And this is a few orders of magnitude larger than that obtained from other methods such as pumping or tunnel junctions into metals or semiconductors. And so the first piece of work showed that efficient spin injection into a semiconductor is possible. We overcame the impedance mismatch problem because we made use of the far out of equilibrium nature of our electrons, and we got a giant spin current density that is larger than what other people got there. So this is part one of our work. For part two, instead of a semiconductor, we went to a semi-metal, and it is actually a direct semi-metal, which is a platinum diselenide, which is central symmetric, where the direct point is about 1.2 eV below the Fermi level. And because this is a central symmetric semi-metal material, we should not expect any second-order nonlinear optical effects. And so, but we still went ahead to do this experiment. And so we were able to pump the sample from normal incidence to oblique incidence. We were able to obtain not just the Y component or the in-plane component of the emitted Terahertz electric field, but also the out-of-plane component, which we call XZ. And take note that this platinum diselenide sample is actually a polycrystalline, not a single crystalline thin film. So observation one, we pump at normal incidence. We don't get anything, which is what we expected. And when we pump at oblique incidence, the Terahertz is rapidly turned on. So this, and then when we change the incident angle, you can see here for small angles, it is roughly linear. And so this observation tells us that perhaps the Terahertz emission is enabled by the photon momentum, which suggests that this Terahertz emission mechanism is photon drag. We went ahead to adjust other knobs. So we use linearly polarized light, and we pump at minus 20 degrees as well as plus 20 degrees. So as you can see, going from minus 20 to 20, all that we change is the direction of the photon momentum. And you can see here for both the XZ component and the Y component of the emitted Terahertz pulse, you can see that there is a flip. It flips from here to here, and it flips from here to here. So this is so both the EY and EXZ were reversed when theta I is reversed, and that is when the in-plane photon momentum Q reverses direction. So this is consistent with photon drag. Now, what if we use circularly polarized light? We see the same thing. You can see here that there's a flip from negative to positive, and there's a flip from negative to positive. So the conclusions are the same. And once again, when we change the incident angle, we also change the magnitude of Q, and so we also it's consistent with photon drag once again. And so the next thing that we did was we rotated the azimuthal angle. So we fixed the incident angle at minus 20 degrees. So we fixed the direction of Q, and we just rotated the sample this way. And as you can see, as we change the sample azimuthal angle, there's hardly any change in the emitted Terahertz waveform. So once again, it shows that the emitted Terahertz waveform is locked to Q, not locked to the azimuthal angle. We measured the Terahertz peak amplitude as a function of pump power. And so we found it's linear with pump power. So it is consistent with a second order nonlinear process. Next, we varied the pump polarization. And we found that, you can see here that EXZ stays positive, but the modulation is quite large. Whereas EY is not just a very large modulation, but we can actually change the sign of the polarity of the terahertz pulse. And so in principle, we can choose theta P to maximize or minimize the different components of the emitted terahertz pulse. For example, if I were to choose 90 degrees here, you can see that the total terahertz intensity is very small. What about palm helicity? So if we were to use circularly polarized light instead of linearly polarized light, once again, the XZ component stays positive, and the Y component it can go from a very large positive to a very large negative value. We fit it with this phenomenological model, and we actually found that the circularly polarized light affects EY a lot, but circularly polarized light here doesn't really affect EXZ. And so we can, in principle, once again, we can choose alpha to maximize or minimize the Y component of the emitted terahertz pulse. So the next question is, could this large modulation with linear polarization and helicity be due to the fact that as you vary these, as you vary theta P or alpha, that the absorption of the sample of the light by the sample has a large difference? And the answer is no, because when we measured the reflectivity of the sample as a function of the polarization angle and the quarter wave plate angle, we found that the change is only about 20%. So there is a suggestion that perhaps this large terahertz modulation is caused by quantum geometry. That is, at different points in the Brouwer zone, the transition matrix element is different, and so there's the sampling of these matrix elements is asymmetric in momentum space. And how many minutes do I have? 5. 7, huh? Okay. Okay. So I don't have much left to say, but you can see that from a previous theoretical work by a Japanese group, they found that for samples, there's symmetric under PT. The kind of photocurrent that's allowed is the linear injection current and the circular shift current. And so from our data, we can actually see that the Y component here of the photocurrent consists of a shift part and the injection part, but the X component, that's only the injection part. And so the C term, which is the shift current, is activated by circularly polarized light, as we can see here, is in the Y direction, but the injection current, which is the L term, is activated only by linearly polarized light and lies along the XY plane. We then went on to calculate the terahertz emission efficiency normalized to sample thickness. And we found that the efficiency eta is of the order of 10 to the 10, which is much larger than other central symmetric materials, and is comparable to the non-central symmetric tantalum arsenide. And so it's quite interesting that a central symmetric material using via the photon drag effect can give such a large second-order non-linearity compared to non-central symmetric materials, which supposedly giving it should give much higher second-order effect. So this is my summary that we can get very large Terahertz emission from this central symmetric material, which is polycrystalline. It is locked to the in-plane photon momentum, and the large Terahertz efficiency may arise from a non-trivial quantum geometry. And this point about polycrystalline is quite important because a lot of time we think that we need something that's super high purity, single crystal, but yet in this polycrystalline thin film that we have, we already get a very large Terahertz emission. So the future direction would be to perform DFT and to perform a finite Q photocurrent calculation. So recently, our theory colleagues did a photocurrent calculation based on the photon drag effect and taking into account the symmetry of our sample. And so you can see that this is our data, and this is the simulation. So you can see that the trends can be reproduced as before. And so, so most of this work, both pieces of work were actually done by my former PhD student come postdoc, Cheng Liang. He's now a professor in China, in UES TC, and samples were obtained from different colleagues in NTU, which is my university, and the other universities are NUS, National University of Singapore, as well as a research institute of Singapore called A*STAR. And I'm very grateful for the enormous contributions from my theory colleagues, especially Marco and Justin. Yeah. Thank you very much.